Okay, guys, I'm back to another whiteboard type session in this podcast. You've had a chance to read that article about specific heat. As you've noticed in your life, there are some materials that heat up really fast, but they also cool off really fast. Aluminum is an example of that. There are other substances that heat up very slowly, and then they give away their heat very slowly as well. And water is a really good example of that. Think about a lake in the fall or early winter. There can be snow all the way around this lake, and yet the lake hasn't frozen. That's because the water has a unique ability to retain or keep the heat that's in it, and so it gives heat off very, very slowly. The same thing's true in the springtime. The snow's all melted, but it's possible that the lake could still be frozen. That's because the water takes a long time to get rid of or to gain the heat energy necessary for the ice to melt. That capacity of an object to either gain or lose heat quickly or slowly is called specific heat. The technical definition is specific heat capacity is the amount of heat necessary to raise 1 gram of the substance 1 degree Celsius. So in class last week, the last activity that we did was we had 5 different substances that all those substances started off at the same temperature. So we had a pan of boiling water, and those metals were down inside of there. There were 4 different ones, plus I also added to that H2O. So we had stainless steel, zinc, copper, aluminum, and H2O. What we want to do is calculate the specific heat for each of these metals. The way we're going to do that is use a mathematical formula, but let me talk through the formula first so that it begins to make some sense to you. So I used this term in class the other day, but let me give it to you again. You started off with a water bath. That was the water that was in the styrofoam cups to start with. And we had a specific amount of water that Sierra measured out for us, and that was exactly 100 milliliters of water inside this bath. Then to that bath, we added an object that had heat energy in it because it was in this pot that we had the boiling water in. So we had the zinc, the copper, and the other substances over here. Each of those, I'm going to divide this in 2. Each of either the water bath or the object over here had a starting temperature, which we'll call the initial temperature. And then it had an ending temperature. And that's the same thing over here. So I'm just going to put IT for initial temperature and ET for ending temperature. Okay? You found the beginning temperature of the water bath, and I don't know what it was. I'm just going to make some numbers up here. Let's say it was 15 degrees Celsius, and then the ending temperature after you put the hot piece of metal in there, maybe it was 20 degrees Celsius. So we have a change in temperature of 5 degrees Celsius. Change in temperature, we use this little symbol here. It's like a triangle. It's called delta T. That's the change in temperature, and we'll say that was 5 degrees. So then on the other side, we're also going to need to calculate the metal started at a high temperature at about 95 degrees Celsius, and it went down to whatever this top temperature was right here. So in my example, that would be it went down to 20 degrees. That's a delta T of 75 degrees. Okay? We're not worried about whether that is a positive or negative at this point. So let's go back to our 2 substances. We have the water bath that gained heat energy, and we have the metal that lost heat energy. So the amount of heat energy that was gained over here is going to be equal to the amount of heat energy that was lost over here. But it's a little bit more complex than that because we need to take some other variables into account. And what we need to take into account is this formula right here. We need the mass on this side times the specific heat times delta T, and that's going to represent the heat gained over here. And then on the other side, we'll do the same thing. We need to know the mass of the metal times the specific heat times delta T, all right, the change in temperature. Now, on this side, we actually know what all of these numbers are. We had 100 cubic centimeters of water, so that means we had 100 grams of water. Remember back when we said that 1 milliliter of water is equal to 1 gram of water. We do know the specific heat of water. You read about that in your reading, and it's 1. And then we do know the change in temperature of the water bath. My example from the other page was 5 degrees, so that would be 5 right here. On the other side of the equation, we do know the mass of each of the metal pieces. That's 56 grams. And we do not know specific heat. We're trying to calculate for that, so we could just leave it as a C. And we do know the change in temperature starting at 95 all the way down to 20, so that change was 75. So let me plug that number in here, 75. So now, if I multiply this out, that's 5 times 1, or 100 times 1 times 5, that's 500, is equal to 56 times 75 is 4,280. 4280 C or X, it doesn't matter, is this. So I solve for C by dividing this side by 2280, divide this side by 4280, and I get 0.1116. I could round that off to 0.12. So if you go back to the book and take a look at the metal, you already know what the answer should be, so you can see how close we actually came to calculating the specific heat. In this particular case, 0.12 could be pretty close to iron or that stainless steel, and so I don't know. I just made that up on the other side, but you need to do the same thing here. The one number that we don't know is the ending temperature for each of your containers, so you're going to need to post that on the discussion area because we need to know what was the ending temperature for the zinc, what was the ending temperature for the stainless steel, for aluminum, for copper, and then I will also post on the discussion area the ending temperature for the water bath. Once you have those numbers, you'll be able to calculate your delta T's and then do the math for each one of these. So come to class next week with specific heats calculated from the investigation that we did for each of those substances. Okay?